Well, good evening. I want to welcome you to our Physical Science 210 live webinar this evening on the topic of the Grand Canyon, a Young Earth View. I want to welcome everyone from LU, and some of you are enrolled in the Physical Science 210 course, which this webinar is hosted by. But some of you are in Creation Studies or the Astronomy course, so we welcome you along as well. This topic coincides in Physical Science 210 with weeks 3 and 4 in the spring D term, and weeks 11 and 12 in the A term version of the course. But it also will apply to week 7 in D term when students are asked to write a comparative essay. So we welcome all of you this evening. There is a way for you to ask Dr. Austin a question, and that's by using the Q&A dialog box that is the interface, the WebEx interface, is on the far right of your screen. And you should all be viewing the opening slide in Dr. Austin's presentation this evening in the main part of your screen. So having said that, I'd like to open us in a word of prayer. Heavenly Father, we thank you for your creation, and we thank you, Lord, for the insight and the wisdom and the understanding that you've given Dr. Austin about your creation, and in particular the Grand Canyon and what it tells us as a story. So we're just thankful tonight to you, Lord, and we just invite you into this time to speak to us and give us the grace to learn. In Jesus' name, amen. So I'd like to introduce our guest speaker tonight, our guest presenter, and we're very honored tonight to have Dr. Steve Austin. Steve is a field research geologist with a PhD from Penn State University in sedimentary geology. He has performed geologic research on 6 of the 7 continents of the world. His research adventures have taken him by helicopter into the crater of Mount St. Helens volcano, by bush plane onto the glaciers in the high mountains of Alaska, by raft through the entire Grand Canyon on numerous occasions, on horseback into the high Sierra, and by elevator shaft into the world's deepest coal mines, by scuba gear into the Great Barrier Reef of Australia, by rail into the backcountry of Korea, by foot onto the barren plateaus of southern Argentina, and by four-wheel drive into the remote desert areas of Israel, Jordan, and Saudi Arabia. Steve is the author of 3 books, 3 videos, 1 computer software package, and more than 30 technical geology papers. Dr. Austin's field research within the Grand Canyon, which is our topic tonight, includes over 400 nights camped out below the canyon's rim. He has launched 22 raft trips within the Grand Canyon, probably more by now. He has explored very remote areas of the Grand Canyon by mule, helicopter, and ATV. His book, Grand Canyon, Monument to Catastrophe, and his DVD, Grand Canyon, Monument to the Flood, summarize his investigations. He has over 10 technical papers on the Grand Canyon alone. Subjects of his technical publications on the Grand Canyon include lava dams, breached dams, fossils, limestones, sandstones, basalt, diabase sills, and radioisotope dating. He is widely known for his discovery of the regionally extensive mass kill and burial bed within the red wall limestone about 2,000 feet below the canyon's rim, which is also one of his current research projects. Dr. Austin finally is affiliated with numerous professional organizations, including the Geological Society of America, and he's, I think, the founder and one of the research associates at Logos Research Associates. So having said all that, it's an honor to turn it over to you, Steve, and I'll let you take it from here.
Well, thank you, Tom, and it's good to be talking to you about one of my favorite subjects, Grand Canyon. And, you know, I've spent a large amount of my life in the Grand Canyon, believe it or not, over a year camped out inside the Grand Canyon. and that was a work experience for me, believe it or not. However, you want to say it, I've been in the Grand Canyon a lot, and I continue to go back and look. What is it that makes Grand Canyon so unique? It's been called one of the 7 wonders of the natural world. And I guess when people rank the natural wonders, I think most people put Grand Canyon at the top of the list. There's just something amazing about the Grand Canyon. What is it about the Grand Canyon that makes it so fascinating? Is it the size or the scale, the perspective, the colors? Whatever it is, Grand Canyon is fascinating. The south rim of the Grand Canyon's almost 7,000 feet above sea level. The north rim of Grand Canyon's about 8,000 feet above sea level. The Grand Canyon's 4 to 18 miles wide. The canyon is something like 257 miles long, counting the upstream portions of Marble Canyon. So only a fraction of the canyon have I experienced, a small fraction, and yet there it is. It's just marvelous. What about it fascinates me? It's layers of rock strata. You see the layered appearance, many flat layers in the upper part of the canyon, 4,000 feet of thicker strata, and then there's diagonal tilted strata in the Grand Canyon. And then you see plateaus within plateaus and side canyons that are colossal, like 10 to 20 mile long side canyons. And so it's something marvelous and something you definitely want to experience. And definitely go to the rim, the South Rim. 5 million people come every year. There's strata in the Grand Canyon that fascinate me, even those diagonally tilted strata. And as we look at the canyon itself, about 900 cubic miles of material has been eroded just to form the erosional profile of Grand Canyon. So Grand Canyon is colossal by any scale. Let's take a look at the pieces of Grand Canyon. I've got this little come together graphic. Take a look at the different pieces of Grand Canyon. Let's put them together, and I've got 5 different pieces that make the outline of what we're going to do today. Grand Canyon, call it a young Earth creation view or creation in the global flood. 5 million people come to Grand Canyon every year, and most of them hear about deep time or think deep time. As I look down in the strata layers, they look at the bottom and sometimes think about the primitive Earth, what the primitive Earth was like. One of the major icon things about Grand Canyon is the way the strata were deposited in calm and placid seas, and then the whole notion that the Colorado River cut Grand Canyon over millions of years. That's how Grand Canyon has become an icon for deep time, primitive Earth, placid seas, slow erosion. Who has not been told the story that Grand Canyon was eroded by the Colorado River during millions of years? That's been in grammar school ever since I can remember, and maybe you too. But you think about it, the Colorado River, almost trivial in scale compared to the canyon itself. Did that cut the canyon? Of course, the myth is of our culture, the icon is the Colorado River cut Grand Canyon during tens of millions of years. But is it true most geologists now have junked that theory, and they're going to very unusual, outside-the-box kind of explanations. And although the Colorado River would seem like it did cut the canyon over millions of years, most geologists now have gone to other theories. Grand Canyon is a marvel, and we need to consider and take into consideration the things that we've been told. Is it deep time? Is it primitive Earth? Is it placid seas and slow erosion? All of those can be challenged, believe it or not. I've been involved with the deep time question, wrote a book called Radioisotopes and the Age of the Earth. And my chapter in that book was, do radioisotope clocks need repair? Testing the assumptions of isochron dating using potassium argon, rubidium strontium, samarium neodymium, and lead isotopes. I spent about $250,000 on doing isotope analysis of Grand Canyon rocks, and I came away believing that radioisotope clocks need repair. They don't give conclusive evidence of the age of things. In fact, there are radioisotope methods that seem to indicate just thousands of years, not billions of years, for the basement rock of Grand Canyon. Well, there's the block diagram of Grand Canyon. You see down in the lower part, over here on the bottom left, you see Zoroaster granite, Vishnu schist, the basement rock that forms the continental crust underneath northern Arizona. Then you have the diagonally tilted strata in Grand Canyon, Bass, Hakatai, Shanumu, Ducks, Cardenas, Nankoweap, and some other formations up above, about 13,000 feet of diagonally tilted strata. And then there's this great unconformity, an erosional surface on those diagonally tilted strata. And then you see the flat-lying strata, beginning with Tapeats, Bright Angel, Muav, Temple Butte, Redwall, Supai, Hermit, Coconino, Toroweep, and Kaibab. And the Kaibab limestone forms the rim of Grand Canyon. And that's the general block diagram giving you the perspective of what the geology of Grand Canyon looks like. And of course, in the inner gorge of Grand Canyon is where the Colorado River is. There's the diabase sill that I dated using the radioisotope methods and got inconclusive results, convincing me that radioisotope clocks need repair. Well, let's talk about the 5 pieces for understanding Grand Canyon. And these are the pieces. And believe it or not, the 5 pieces have my first name. And so S-T-E-V-E, the five letters that give you the introduction to the pieces. The first S is, and there's the pieces coming in. Okay, the first S is sedimentation. And the process of sedimentation is what has formed the strata of the Grand Canyon. In the Grand Canyon, we see layers of sandstone, limestone, and shale. Those are the primary rock strata. And those that formed by the process of sedimentation. And those layers were formed by liquids. And so they're real interesting for consideration. That's my specialty in geology. The T stands for tectonics. Tectonics is the process that deforms, that folds and faults and breaks and crushes the earth. Tectonics is a blacksmith term from Greek. And so tectonics, the process that deforms and folds and faults rocks. We see an uplifted plateau 1.5 miles above sea level. Isn't that interesting? And it implies tectonics. So then the first E stands for erosion, and boy, the Grand Canyon is a monument to erosion, isn't it? And erosion on a colossal scale. Not just the canyon profile itself, the 900 cubic miles of material has been removed to form the Grand Canyon proper, but the plateau, north and south rim of the Grand Canyon has been eroded. So thousands of cubic miles of material has been eroded. An erosion process, very interesting to consider. And then the V stands for volcanoes. Volcanoes. And we see on the rim of Grand Canyon volcanoes, and around the Grand Canyon volcanic process very readily. And then the last E stands for exponential decline. Exponential decline, and you see the idea of slowing down of the processes that formed the Grand Canyon. I bought a new car, and the value of the new car is an exponential decline. When I drove it off the car dealership, then it loses its value very rapidly, and that's a symbol or a way of thinking about how process has changed through time. Process rates have changed through time. The present is not the key to the past. Exponential declining rates is key to the past. You know, Mount St. Helens erupted in Washington State on May 18th, 1980, and it created a whole laboratory for the study of catastrophic process. And my other favorite place to be on Earth is Mount St. Helens, not just Grand Canyon, but Mount St. Helens. And these pyroclastic flows at Mount St. Helens after the eruptions and during the eruptions at Mount St. Helens show some very interesting things. Here is a cloud, a slurry of volcanic ash and steam that's like an avalanche falling out of the crater at Mount St. Helens. And as the pyroclastic flow stops, it freezes rapidly, and you can see, looking at the surface there north of the volcano, the pyroclastic flow deposits. And the flow deposits at Mount St. Helens formed at about 100 miles per hour as the grains of that cloud collapsed and froze rapidly. And you see the pyroclastic flow deposits at Mount St. Helens. Here's the upper part of 25 feet of the deposit, and you can see layering. I thought that layering would form slowly, like between summer and winter, between wet years and dry years. No. Boundaries and stratification can form rapidly in hurricane velocity moving flows. That's what we see at Mount St. Helens. Even thin lamination can form in a hurricane. Can you believe that? There it is. That was sky before the eruption in 1980, and now it's sitting there laminated. Grain flow is able to segregate coarse and fine particles, making that amazing feature we see. This is a flume experiment with a glass window. Sorry, get back to that. Yeah, in this flume experiment, water was moving over the, flowing over the bottom of the flume, and through the glass window, you can see how the sediment migrates and forms these dune-like structures. The migrating dunes make very interesting stratal layers. And those migrating stratal layers can be made by a current of about 0.5 meters per second, maybe 1 or 2 feet per second current velocity in our laboratory scale models. These layered deposits can form very rapidly. And of course, they remind us of the layers in Grand Canyon itself. here is a cliff, north rim of Grand Canyon, and you see this very beautifully exposed, but it can be made by the same process of dune-like features on the bottom of flowing water moving over a flat surface. You see how the dune-like structure migrates, and it makes this diagonal layering within the layers. And that's evidence of powerful water current. In the scale we're looking at, maybe a meter per second flow velocity. And imagine a whole ocean moving at that incredible speed. To Pete Sandstone in the bottom of Grand Canyon, I used to think it took 35 million years for that to form. 350 feet thick, the sandstone layer here in the Grand Canyon, that can form rapidly. At least the bed form that we see can be made in minutes, not millions of years, in flume experiments. And grains can segregate rapidly simply by pouring. And I made a laminated deposit of sand in this laboratory experiment. You can see how they accumulate rapidly. How do mud rocks form, the fine particles of mud that form the shale layers? The old idea is they form as dispersed particles and settle onto the surface very slowly, like it might take 2 or 3 days for a mud particle to fall just 1 foot through water. The idea of vertical fall of particles implies that muds must accumulate over an immense period of time. But in the laboratory, we can make mud particles flocculate and form clumps, and the clumps can come at through the tank at 15 degrees to horizontal, and you can accumulate mud beds very rapidly using this process. There's a racetrack flume, which is a type of device that makes a circulating current, paddle-driven, so it dampens turbulence, and it allows mud to form very rapidly in layers. Maybe a millimeter per second accumulation rate in the flume experiments. And you can see the laminae which have formed rapidly, and this whole idea of rapidly accumulated mud is causing what we call the mud rock revolution. We have very significant evidence in mud layers of this ripple lamination, which is formed in the flume experiments. The mud rock revolution, stratification next to volcanoes in modern lakes on continental shelves today form very rapidly. Stratification in flume experiments forms very rapidly. And then mud rocks, that's what we see in Grand Canyon, they're dominated by the structure of rapidly deposited sediment. And so time is not a magic wand you wave and it creates things incredibly slowly. Time is the villain of the plot. When we actually look at the sedimentary process, and the process of sedimentation, it forms rapidly. The mud rock revolution, fine sediment is seldom deposited as individual grains, but commonly organized into grain aggregates. In other words, it falls fast. These studies indicate that many of our preconceptions about fine-grained rocks are naive. And Bohack and McQuacker Science Magazine, they say mudstone science is poised for a paradigm shift. Of course, the old paradigm is slow and gradual, calm and placid seas. Well, a guy named Dave Sturm said, Steve, you've done a wonderful job showing how particulate rocks like sands form very rapidly and leave layers. But don't you ever think about explaining the Grand Canyon limestones that way, because there we have proof positive of calm and placid seas over millions of years making strata. petroleum geologist in Bakersfield, California, it was a challenge. So I started studying limestone, and in the Grand Canyon, I found this 7-foot thick limestone layer. You can see it right there. It's a thick, massive bed of limestone overlain by thin chert and limestone strata right here. And in that stratum are nautiloids. A nautiloid is a squid-like extinct creature like a squid which had a solid chambered shell. And the nautiloids are about the length of your arm, and I have found thousands. I've drawn pictures of thousands, and there may be billions of fossil squid in Grand Canyon with the shells still intact. They're all in this one layer. You can see what they look like, cross-section of the shell. You can see the pressure chambers, the body of the animals over on the left side, and they have orientation and other things indicating they were swept up in a current. And it's highly addictive. I love finding nautiloids, and I go there. Looking at the Redwall limestone. Redwall limestone in this canyon called Jeff Canyon behind me shows an extraordinary sequence of strata. We see the thick-bedded limestone strata overlain by thin-bedded limestone and chert strata. This boundary defines the location where we find the nautiloid bed. The uppermost thick bed behind me is the nautiloid bed. This is where we've discovered all the nautiloids here in Grand Canyon. Boy, did we study and find a lot of nautiloids. First started over here at point 1. That's called Nautiloid Canyon because it has 80 nautiloids on a limestone ledge. And I have followed the nautiloid layer through the whole Grand Canyon out into the central Grand Canyon, out to the western Grand Canyon. Then I followed the nautiloid layer into the Lake Mead region in Nevada, and then eye level with the Stratosphere Hotel in Las Vegas, Nevada, right on Frenchman Mountain, there's nautiloids. And so about 150 to 200 miles long, something like that. You can imagine this layer. And nautiloids were swept up in some kind of current. Here you can imagine the idea. Underwater mud flow, essentially, swept up the marine creatures and then buried them rapidly. It took something like a mud flow, and here's a mud flow at Mount Pinatubo volcano in the Philippines in the 90s. These fast-moving underwater mud flows could bury the nautiloids. Here's a terrestrial mud flow down a valley. And I'm Mud Flow Man. That's my my email address. So anyway, how did all the coarse fossils get in the middle of this limestone bed? It's catastrophic water deposition on a colossal scale. And then the recoil of the ocean made the thinner chert and limestone layers above it. Imagine 25 cubic miles of slurry coming over Grand Canyon, flowing from Colorado into Nevada and California across Arizona, depositing those nautiloids, and then imagine the recoil of the ocean as it comes back. Rapidly moving sediment flows. Minutes, not millions of years. Modern observations and flume experiments have revolutionized sedimentation, thinking the understanding of strata deposition was a very catastrophic process. That's kind of the takeaway with sedimentation. It's a very catastrophic process, and we need to understand it as we look at the fossil-bearing coarse and fine mud, sand, and lime layers. Okay, let's talk about the T in the outline T, sedimentation, and then we follow that with tectonics. Tectonics is the process that breaks and folds rocks. you've probably heard about California. California's been sliced by the Great San Andreas Fault, but the Pacific Plate has collided with North America Plate, creating the leading edge of the Western North America, and that's tectonics on a marvelous scale. It's a glancing blow, kind of a sideways collision in California, but it's head-on with Alaska. And Alaska has accreted ocean floor against southern Alaska by head-on collision. And so if you want to see tectonics of Western North America, Alaska is a great place. And what a marvelous place to see. Here's the glaciers coming down into the ocean, 18,000-foot mountain range in the background. There you see the ocean floor rocks, the Nikolai Greenstone, which is docked against southern Alaska. It's ocean floor that's been pushed into and even subducted or shoved underneath Alaska, underneath the leading edge of southern Alaska. You can see the faults and the way the strata are bent. It's a compression. It's a head-on collision. And the head-on collision created all of these accreted rock formations that are welded or docked onto southern Alaska. What a place to go study. But you can study how rock was accreted into the southern part of Alaska, and you can study how the lithosphere, the ocean floor, slid under Alaska. That's called subduction. The process is called subduction. And strong subduction of the past brought great terrains and accreted them onto southern Alaska. And there were big volcanoes and giant earthquakes, of course. And the Pacific Plate was shoved underneath southern Alaska in the past. Today, we have weak subduction, or subduction that's largely stopped. The ocean floor is no longer being shoved down underneath Alaska with the lighter rock attaching to southern Alaska. It's basically stopped, largely stopped, and we have the weak subduction in the small volcanoes of the present. And so declining tectonics with time. Strong subduction of the past melted rock in faults. Rock slipped maybe 100 meters or hundreds of meters along fault surfaces, and they did it very rapidly. That type of faulting doesn't occur today. Magnitude 8 and 9 earthquakes usually have less than 100 feet of displacement. Enormous molten bodies called plutons were intruded in the past, and there were enormous volcanoes. And of course, we had the uplift of 18,000-foot high mountains in southern Alaska. Now we have the weak subduction of the present. We have broken rock, not melted rock on faults. The heat generated by the fault is not as significant as in the past when we were able to melt rock. Small dikes and sills, small volcanoes, and low mountain ranges along the immediate coast in southern Alaska, low mountains and the ocean trench that's there today. Here we are looking at one of the faults, and we see in the fault, it looks like coal in the fault, and what is it? It's glass, and it was melted rock in a fault. And it, no modern earthquake, magnitude 7, 8, or 9 earthquake makes liquid melt in the fault surface. It pulverizes or fragments the rock into powder. It's friction that doesn't generate enough heat because of the length of displacement being short that doesn't melt rock. Under the microscope, you can see the melted structure of rock. And so the melted structure in rock in ancient faults argues for what we call a super fault. So melted rock, what's called pseudo-tachyte in the geologist's vernacular, is evidence of a super fault. A super fault is a big fault, like makes magnitude 10 or 11 earthquakes that we've never experienced, that type of thing. Super fault requires a super quake. A super quake leads to the idea of super tectonics. Super tectonics, if it occurs around an ocean, creates a super flood, which what? Requires survival by boat. You can see catastrophic plate tectonics leads to a global flood, a super flood, and survival by boat. That's the way to think about that. And of course, all of the southern Alaska tells us that. Mountain ranges everywhere show collapse features from tectonics. And of course, the plateau in Arizona is uplifted above sea level. There it is, the plateau, 6,000 feet above sea level on the south rim of Grand Canyon, 7,000 and 8,000 feet elsewhere. A man named Antonio Snyder wrote a book in French, La Création et les Mystères dévoilés, the Creation and its Mysteries Revealed. He argued that the continents split apart during a global flood. 1859 he published. It was a bad year for catastrophic plate tectonics because Darwin published his book. People didn't want to hear another apologetic about how the flood formed the distribution of continents. Of course, that was slowed down and made continental drift, and but it was continental sprint in the past. Tectonics, strong subduction of the past, preceded the weak subduction of the present. And Grand Canyon's a plateau, a mile and a half above sea level. Imagine the energy it took to uplift the plateau. Colossal tectonics. And then you see erosion in the canyon. In Mount St. Helens, there were mud flows that came out of the crater. On March 19, 1982, a mud flow came out of the crater and breached a dam of landslide material and cut through ancient lava flow rock. Here's a canyon over 100 feet deep, eroded rapidly after the summer of 1980 by mud flows. And here's where the mud flow of March 19, 1982 broke through a debris dam, and it created a miniature Grand Canyon, 1/40th scale. You see the gully-headed side canyons, the cup-shaped side canyons. The breach did not occur straight through. It has a snaky path, and it just reminds me of the Little Grand Canyon. And so we've actually called that the Little Grand Canyon of the North Fork of the Toutle River at Mount St. Helens. A catastrophic breaching event makes terrain like you see in Grand Canyon. And of course, Grand Canyon is the world's premier example of some type of breach. And I believe it was lakes to the east of Grand Canyon, Hopi Lake, a lake at 6,000 feet elevation up against the Kaibab upwarp, breached its dam, and another lake or series of lakes, maybe involving thousands of cubic miles of water, drained off the saucer-shaped depression formed by on the top of the Colorado Plateau. The plateau was formed. It didn't have a river system. Then the river system was created by the drainage of lakes. That's the breach dam explanation for the Grand Canyon, erosion of Grand Canyon. It's a theory that geologists are talking about. And there's bedrock erosion canyons like in southeastern Washington State, where Lake Missoula flood, a glacial lake in Montana, breached its dam. And here's a canyon over 400 feet deep. Up against the railing on the right side of this canyon are people. You get some idea. That was eroded in weeks by drainage of lakes in Montana. 500 cubic miles of water drained through eastern Washington. Sheet erosion, that's the beveling of the surface, widespread beveling of the past preceded channelized erosion of the present. Okay, and on the, we have the beveled plateau, and then we have the great unconformity, the buried erosion surface at Grand Canyon. Then we have volcanoes. There are volcanoes on the north rim of Grand Canyon. When you think about volcanoes, I think about Yellowstone, the depression that's about 30 miles long over the in Yellowstone Lakes area is a collapsed volcano. Geologists are generally recognize that something like a couple thousand cubic kilometers of magma exploded in some type of super volcano, and then it collapsed to form the Yellowstone caldera. There's Mount St. Helens. Whoops, Mount St. Helens volcano. There it is in Washington State. It had 0.25 or a quarter cubic mile of volcanic ash came out. The last of the Yellowstone eruptions had over 600 cubic miles of volcanic ash. And there's evidence in the dinosaur beds of volcanoes that belched out about 4,000 cubic miles of ash. We have super volcanoes of the past, and we have small volcanoes of the present. Volcanoes illustrate the declining power of eruptions with time. Mount St. Helens is just a small to average volcano from the standpoint of human experience and history. There's been colossal eruptions in the past. The power of geologic process was great during the first 3 days of creation week when God made the continents and the ocean basins. And then the power of geologic process was high during the global flood, during the year-long global flood in Noah's day. And then the power of geologic process has decreased with time. And that's the idea of exponential decline, declining power with time, declining power of sedimentation, declining power of tectonics, declining power of erosion, declining power of volcanoes. So the years after the flood, and fortunately we live in a time of grace when we don't have colossal explosions. And that's referred to in 2 Peter chapter 2, 2 Peter chapter 3. In the last days, Peter says there will come mockers. They'll say all things continue as they were from the beginning. In other words, slow and gradual process. Peter says they are willingly ignorant of this, that by the word of God the heavens existed long ago, and the earth was formed out of water and by water, probably reference to creation week. God spoke the world into existence by his word, and it was formed out of the water on day 3 of creation week. And then Peter says, through which the world at that time was destroyed, being flooded with water. And that's the graphic language in Greek of the cataclysm of the global flood. So a global flood seems to form the framework of Peter's thinking, and this is a prophecy about the last days to be remembered by the church. In the last days, scoffers will come, saying all things continue as they were from the beginning, in other words, slow and gradual, and Peter refutes the latter-day scoffers by pointing to creation and the global flood. Exponential decline. Geologic processes were greatly accelerated in the past and have slowed significantly, telling a general story of exponential decline. Okay, we got the 5 pieces for understanding Grand Canyon. And can you give these back to me? What is the S? The S stands for, well, let's put the pieces together. We got 5 pieces we got to put together to get a really good perspective view of the origin of Grand Canyon. The S stands for sedimentation, and the T stands for tectonics. The E stands for erosion. The V stands for volcanoes, and the last E is exponential decline, reminding us of how the past has changed. There are the 5 pieces for understanding Grand Canyon. Grand Canyon is a monument to creation and the flood. We see something of Creation Week. We might see day 3 of Creation Week in the sedimentary strata, even in the formation of ocean basins, maybe even a pre-flood delta, as northern Arizona appears to have been underwater before the flood, and then they flood on top of that. That's an amazing thing, the Grand Canyon. A global flood. The waters were upon the face of the whole earth, Genesis 8:9. All the high hills under the whole heaven were covered. Universal language, Genesis 7:19, regarding the global flood. The world that then was being deluged with water perished, 2 Peter 3:6. Okay, well, I've given you a perspective on Grand Canyon, and be sure and watch for rocks. Think about the creation, fall, flood framework of Scripture when you look at the earth, and it's been wonderful to share Grand Canyon with you here at Liberty University.
Great. Steve, thank you very, very much. And if you don't mind, I'd like to just ask you a couple questions based on your presentation. Beginning with the RATE project and the book you referred to where you authored some of the chapters, could you just describe to us what motivated you to spend $250,000 on getting lab age estimates for those volcanic rocks in the Grand Canyon, and maybe give us a couple examples of some of the specific inconsistencies of those dates that you found out during that project, and kind of what was the scope of the project? I understand it took place over several years. Would you mind addressing that?
It's a 7 or 8 year project that I was involved in, and fortunately the Lord gave us funding, and we committed to doing dating of Grand Canyon rocks. I think I've spent more money on dating Grand Canyon rocks than anybody else on Earth. Anyway, boy, spent a lot of money dating Grand Canyon rocks with isotopes. And if everything was the way the deep time perspective, the myth says, those 4 different methods of dating one rock should give one age. So I spent a considerable amount of time dating one rock by 4 different methods. When I did that, I got 4 different ages, from 1.8 billion years down to about 0.845 billion years for the deeply buried diabase sill in Bass Rapids, diabase sill in Grand Canyon. In other words, the clocks are broken. They need repair. And so I think we can explode the myth of deep time being proven by radioisotopes.
Great. Thank you for addressing that. The age of the Grand Canyon itself, the erosional feature of the Grand Canyon, in secular literature, has it changing all the time. I think there's one figure at the canyon itself of something like the canyon's 75 million years old, and more recent literature shows it as being much younger at only 5 million years old. Do you want to address kind of that changing scenario?
Well, the plateau, Colorado Plateau, was largely uplifted during the time of the dinosaurs. That's back about 75 million years ago, in many people's thinking. And but how could the plateau exist for 75 million years and not be leveled down to sea level and not have Grand Canyons eradicate the whole plateau? And so there's evidence that the river is recent. In other words, time is not the hero of the plot, it's the villain of the plot. Now, potassium argon dating indicates that some of the lavas have been dated at 1 million years old that blocked the river that spilled off the rim. Those dates have been exploded, debunked, and I was involved with doing a little bit of that. And now we have geologists talking about, believe it or not, a conference of geologists on the south rim of Grand Canyon in the year 2001. They met to consider the various theories, and the headline, the newspaper headline after the conference was, "Geologists believe that Grand Canyon formed in a fraction of 1 million years." And I can believe it formed in a fraction, a very small fraction of 1 million years. But anyway, it's interesting to see geologists coming out with these rather outlandish and catastrophic theories for the formation of Grand Canyon in defiance of what would appear to be the simple and elegant myth that's been around ever since John Wesley Powell, the first geologist, took a raft trip through Grand Canyon.
You've said 2 or 3 times that the villain of the story is time, and I assume that you're saying that it's the villain of the old Earth perspective. It's interesting to me that geology gave us the time in the beginning, in the late 1700s and early 1800s, with the establishment and acceptance of the principle of uniformitarianism, and it seems now that geology is taking it away. Can you just address, is there anything left of the principle of uniformitarianism? Is there any geologist today that still thinks that things form by slow, gradual processes, because there seems to be so much evidence for catastrophic history in geology?
Well, when I was a graduate student, or an undergraduate student in the 1960s at the major universities, they were saying that uniformitarianism is like a scientific law. It just describes the way the Earth history has been, just slow and gradual. Beginning about 1980, right after I did my PhD dissertation, right after people started wondering about dinosaur extinction as a global event, and then people started looking at sedimentary process critically, did this neo-catastrophist line of thinking come back. Of course, Darwin and Darwin's myth largely swept the catastrophe way of thinking under the rug for 150 years. And now we are realizing we need to sweep the dirt out from underneath the rug. It's lumpy, and so these things, a catastrophic process forms what we really see, which is, we have ocean over the continent, and that's obvious when you look at the Grand Canyon. How many oceans? Maybe just one ocean, and maybe a catastrophic flood. So that sits nice, and so I think of Grand Canyon as a monument to creation and the global flood.
Thank you. I don't know if you can do this without a visual presentation, but can you kind of take us through the rocks of the Grand Canyon and what would be considered pre-flood rocks, what would be considered flood rocks, and what would be considered something after the flood, kind of the story of the Grand Canyon from that, Genesis record.
Okay, I got the graphic up here on the screen. There's Grand Canyon block diagram, and there are basement rocks really deep in the Grand Canyon, granite rock and a mica-rich rock that are metamorphic and igneous rocks. Those rocks, I think, are related to Creation Week Day 1. Mm-hmm. And then I think those are visible in the inner gorge of Grand Canyon places. In other places, we see the diagonally tilted strata called the Bass, Limestone, Hakkatai Shale, Shinumu Quartzite, the Dock Siltstone, the Cardenas lavas, and the Nankoweap Sandstone. That sequence there probably represents the pre-flood world. The Bass, Hakkatai, Shinumu may be Creation Week Day 3 when the ocean basins formed. The water was covering the whole Earth, and then it came back into the ocean basins. Day 3 of Creation Week, the waters were gathered together into one place, and then God said, "Let the dry land appear." Angels probably saw that. Job chapter 38, when the morning stars sang together, where were you when I laid the foundations of the earth? Anyway, in Creation Week, an angel might have blinked, and wouldn't have, might have missed the creation of light, something like that. But 340 million cubic miles of water over the whole planet being gathered together into ocean basins would be a colossal event. I think that's involved with forming these early strata in the Grand Canyon. My personal belief is that there was a sedimentary delta or a shoreline, maybe in New Mexico and shallow ocean over Arizona before the flood. And we see the delta and some of the shoreline deposits, perhaps, in that pre-flood world. And then the beveling of and the tilting of the strata. These strata were tilted in a colossal upheaval. They were tilted and then beveled. And that is probably the erosion that began the flood. So there you see the great unconformity. The great unconformity is global. It's under Virginia. It's under where I'm talking to you right here in Pennsylvania, in Pittsburgh. It's under Illinois. It's under Colorado. I've seen it all over the place. The great unconformity is the beveled surface, probably onset of the flood. And the 4,000 feet of strata probably represent the early and middle flood, and then the retreat of the flood, late flood, beveled the surface, and then in the post-flood period, the saucer-shaped depression of the Colorado Plateau formed. Ponded water on the plateau made these lakes, and there were volcanoes going off, and then finally the volcano, the dam was breached. The saucer-shaped depression overtopped, and like Mount St. Helens, water or mud breached through and cut Grand Canyon recently, not millions, tens of millions of years ago, and not over a period of tens of millions of years. So the canyon, I think it fits nicely into a creation, fall, flood, young Earth history framework.
Excellent.
You like thinking that way? I do.
I do too. I think it tells the story, and never quite heard it put together that way, walking us through Genesis. And I think that's a testimony to
the time. So the present is not the key to the past. If what I'm telling you is right, what? The Bible, or the historical framework of the Bible, is the key to the past.
Wonderful. I'd like just to close, Steve, if you wouldn't mind just sharing some of your product and some of the resources that you have out there, and then just any advice that you might have for people that are interested in pursuing something beyond taking a required course at Liberty in earth science or another subject. What would you recommend for somebody that might actually be interested in becoming a research geologist or going deeper than simply getting their feet wet in this at this level? If you could address that, that would be great.
Okay. Well, let's talk about resource material. There's a lot of resource material out there. My book, Grand Canyon Monument to Catastrophe, is probably the monograph that is most scholarly and probably the college level textbook on Grand Canyon. You might look for that. You might also look for my DVD on Mount St. Helens, Explosive Evidence for Creation, that kind of thing. Mount St. Helens is a miniature laboratory for studying catastrophe theory. Of course, it was one of the things that has introduced geology back into thinking about catastrophic thinking. And so this resource material, global flood, catastrophic process, radioisotope dating, the fossil record. I'm making a documentary on Grand Canyon, come out soon, with Del Tackett, Truth Project philosopher of science. And so some of this material is readily available. So it is a good time to be a catastrophist geologist.
Mm-hmm.
Pinch me, I can't believe it, that, people said that I would be of little value as a geologist espousing a catastrophic perspective on the history of things, and then look what's happened to geology now. Mm-hmm. Catastrophe thinking is breaking out in the various fields, and of course it needs to be synthesized into the biblical framework, I believe. And so we need people to come alongside and the next generation of geologists. Do get geology courses like Liberty University. Marcus Ross teaches some wonderful geology courses, and paleontology, and those are really fascinating subjects. At Liberty University, you've got the science department and quite a few science courses. There's a science major at Cedarville University, a geology major. And the geology major, I teach some of the courses. And I'm adjunct faculty at Cedarville. And so we go on field trips, and we have classes, and we integrate geology into a biblical framework, which is an excellent way to be discipled if you want to go into this field. Take the next step is to get this course material and the basic science prep behind you, and then graduate school. Boy, we need people to solve these problems, understanding how rocks form and understanding the history of the Earth.
Hello.
Hello, Tom.
Yeah. So, Steve, thank you very, very much for your input this evening. There's a couple of students that just used the text box to say thank you as well. So we really appreciate you being with us tonight. This will be made available as a recording for the PHSC210 students. So just on behalf of all the students, let me just say thank you again for just a thorough, great presentation for all of us in the course.
And it's been wonderful sharing my life experience with Grand Canyon, and I look forward to doing it more at Liberty.
Yeah, and you're not done yet. You're actually going to be at Liberty this summer doing a conference. Is that correct?
That's right.
That'll be,
I'll be
I think,
speaking on earthquakes and the Day of the Cross, believe it or not, doing studies on mud and Dead Sea.
Wonderful. Great. Well, that's all for tonight. We appreciate you all being with us, and this will be made available as a recording later on. So the conference, the question just came up, when is the conference? I think it's in late July. So we appreciate it. Someone chimed in, Steve said, an awesome perspective. So thank you again. We're going to sign off now. God bless. Bye-bye.
God bless you.